Okay, so for the second talk for the morning session, we have Matteo Longo from the University of Padova, and he's going to talk about, here it is, higher fitting ideal, on the fitting ideals and the anticyclotomic Shafarevich state groups.
Thank you. Thanks to the organizers for inviting me, giving me the opportunity to talk about this work, which is higher fitting ideas and anticyclotomic Shafarevich state groups. And this is joint work of Enrico Daronche, which is a PhD student in Genova, and Stefano Vigni, which is also in Genova. So let me start with a brief introduction to give you some motivation why we studied this thing. So the motivation of this talk. So we fix an elliptic curve over Q, and we suppose this is conductor N. And we want to understand, so we also let K over Q be a quadratic imaginary field. We always ask that the discriminant of K is prime to N. Okay, so what we want to understand is the behavior of the elliptic curve along abelian extensions of K, which are of anticyclotomic type. So over K, there are two ZP independent linear extensions. One is cyclotomic and the other one is anticyclotomic. And this anticyclotomic extension is the one that I want to consider. So, okay, so for this, we denote K infinity over K. This is the anticyclotomic ZP extension of K. So this means that the Galois group of K infinity over K, that is just ZP. And, if you take the complex conjugation here, this tau, different from 1, this tau acts by conjugation on this Galois group, K infinity over K. So you take a lift of K of tau to K infinity over Q, and the action is by inversion. So it's a dihedral type. So this is sigma to the -1. And this is a lift, actually, of theta. Okay, so this is the extension that I want to consider. And I want to see what is the behavior of the model Weil group, for example, of the elliptic curve over this ZP extension. And well, for this, let me give you some assumptions. We suppose to factor this conductor into coprime integers. So this n plus and n minus are coprime. And we suppose that, so here n minus is the product of the primes, which are inert in K. And we always assume that this is square free, for simplicity. And then n plus is the product of the primes that are split in K. We always assume that the residual Galois representation of the elliptic curve is surjective at the prime P. So we fix prime P. Sorry, I should have fixed it before here. Of course, this is a prime. Fix a prime P. Now this doesn't divide the discriminant of K and N, and such that the residual Galois representation of E to the, well, say, automorphisms of the P torsion of the elliptic curve. So this is just GL2 of Z over PZ. So this is surjective. We assume this is surjective. And for this, we also assume that, so for simplicity, we assume also that E has no CM, so that this surjectivity assumption is satisfied for all P sufficiently large. Okay, so for all except a finite number of primes. Okay, so I fix an elliptic curve. I want it not to have CM, and I take a prime P such that this representation is reducible. I have a couple of other technical conditions which are less important, so we skip them. So this is somehow the crucial one that I'm going to use. And now in this situation, I can consider Selmer groups. And yeah, so and Shafarevich Tate groups, as in the title of the talk. So for this, I'm just giving a quick definition of these objects. So the Selmer group of E over K infinity, this will be the limit, the direct limit over M and N of the P to the N Selmer groups of E over Kn. And sorry, there is an M here and an N there. And this is some subgroup of the cohomology group of H1 of K and E P to the M, the P to the M function, which is defined essentially using local conditions to define the Selmer group. We require that the localization of these classes belong to the image of the local Kummer map for all primes P. So this is just the usual usual groups, and then we consider this X, which is the Pontryagin dual of the Selmer group. So this is the Pontryagin dual. And then we have main conjectures for this. For these groups. So, well, we write ni, we always write ni, nu, for nu of, well, let's say A and K. This is the parity of the number of primes dividing N minus. And this is there are two different situations, crucially, if nu is even or nu is odd. Because this number of parity of primes dividing N minus tells you which is the root number of the complex L function of the L function of the elliptic curve over these extensions here, the generic root number, say. Okay, so accordingly, if this nu is even or odd, you have generic rank 0 or generic rank 1 situations. Okay, so the expectation on the growth of the Selmer group changes drastically in these two situations. Okay, so the first situation I want to consider is the definite situation. So in this case, we require that ni is odd. So we have an odd number of primes dividing this, which are inert in K. Okay, so then in this case, what is known? In this case, well, we know that the L function of E twisted by chi, where chi is some finite order character of this square group, to, I don't know, Q, P star, finite order. So you consider the twisted function of E. So we base change E to K, of course, and then we can take the twist of this function. And this is then known to be non-zero for all K, for all chi, except a finite number. And this is an old result of Atzal. So in this case, what you expect the existence of a p-adical function which interpolates these objects, and that's true. So the second point here is that there exists some p-adical function E over K infinity, which is an element of lambda, which is the Derivas algebra of this G infinity, such that what does this thing do? So if you evaluate at chi, this thing is essentially equal to this p-adic, to this complex L function. So interpolates the complex L values as the Kubota-Leopold more classical thing. And equality up to this point means that there are explicit factors in the interpolation process, which I don't mention, which are, the important thing is that these are different from zero. So this is non-trivial if and only if this is non-trivial. Okay, so then this X is a torsion lambda module. And which can be written as the direct, it's a rank 0. So yeah, torsion lambda module, which is pseudo-isomorphic. To a direct sum of some simple objects, quotients of lambda by this Fi, which are powers P, powers of P, or distinguished polynomials. Which means so monic polynomials of certain degree whose coefficients, except from the first one, are in the maximal, so are divisible by P. Okay, so in this case, the main conjecture tells you that the product of this Fi for I from 1 to n is this p-adical function. The ideas generated are the same up to squared. Okay, so this is the say definite Iwasawa main conjecture in this setting, which expresses essentially this the product of all of this. This is the what is called the zero-splitting ideal as an analytic in analytic terms as a p-adical function. This is a p-adic analytic object, you see. So this can be seen as a p-adic analytic analog of a Birch-Newton-Dyer formula. Okay. In this case, in the definite case, well, this X is torsion, and we define the Shafarevich group to be okay. So maybe I don't need to cross there. So I go here. The Shafarevich group is always the torsion part of this big X. So in this case, this is torsion. This X is torsion, and we define the Shafarevich group of, say, E over K infinity. Maybe there is a better notation for this, but that this is a little bit misleading. But yeah, so maybe I should choose. Sorry? Yeah, sorry, this is theorem. Yeah, sorry. This is a theorem. There are several proofs. Well, one divisibility comes from an old paper of Bertolini and Darmon. Then the full equality comes from the combination of this divisibility with the work of Skinner-Urban, which essentially proves the converse the converse theorem for over K. Okay, combining these two things, we have this equality, and this is a theorem. There are several proofs available. One of them is a paper by Bertolini, Benerucci, and myself, and which okay, there are other proofs. There is a paper of Castella with Kim and with Burungale. With I should first maybe put first. Okay, so these are the some of the two references that I can give you. This one works also for supersingular situations, in which is a different setting that I'm not going to talk about because it would be too technical to explain. But it is possible to redo this thing also in the supersingular case. This is only for the ordinary case, which is exactly this setting here. Okay, so in this case, I would call, let's say, of say lambda of E. Okay, this is X torsion, which is X. Okay, because this is torsion in this situation. Okay, and then let me talk about the indefinite setting. So here I try to be a little bit quicker, but the ni in this case is even. And then, so what we have in this setting, we have that there are this Kn. So the sign of the functional equation, first of all, in this situation of the complex cell function, in this situation does not force the L function to vanish identically. And it is a conjecture that the derivative of the L function, it's not a conjecture, sorry, it's a result of Cornu-Watzal that combined with the Gross-Zagier formulas that this L function does not vanish. But let me say only the things that I need. So let Kn, this is a Nigner point on E of Kn. Yeah, here, maybe I didn't write it before, but this Kn is the sub-extension, which is whose Gara group is Z over P to the N Z. So we have a collection of points here, and these are, thanks to this result of Cornu-Watzal, these are non-torsion for N sufficiently big. This has an implication, which I'm not going to write down. Combining this with the Gross-Zagier formula, we see that the derivative of the L function of L twisted by K, this character, some character of this Gara group, is non-zero. But in this case, what we do is to consider this K infinity, which is the limit, the inverse limit with respect to the co-restrictions, or the norm maps if you want, because these are just points, but we can see this as homology classes with a Kummer map. I always identify the two symbols, K, N, and the p-adic Tate module of E. Okay, I need to pass through P, K, and tensors P to land down here. Okay. So I identify Higner points and their homology classes that I define, and I can take the co-restriction maps of this Kn, and I get something in the limit of this Selmer group of, say, limit in N and M, if you want, of P to the N E over Km. Okay, so this is just the inverse limit of these Tate modules here, and the Selmer groups inside there, and which I call this inverse limit as P hat. Okay, so and here the inverse limit is as usual with respect to the co-restriction maps and with respect to the multiplication by P to get the Tate module, which is the definition of the Tate module. Okay, so these are the canonical maps that you have in cohomology and in the definition of the Tate module as inverse limits of the P to the n torsion. Okay, now this situation X, this is the same as before, so I'm not going to rewrite it, but it's just this Selmer group, the Pontryagin dual. This is a rank 1 lambda module, and we'll look at its torsion part. So it can be written as X can be written as a pseudo-isomorphic as before to lambda plus some lambda over Fi with the same meaning as before. So these are distinguished polynomials or powers of P. And we define, in this case, the torsion part of this to be the Shafarevich Tate group. This is, well, X tors. It's the torsion part of this. And what we know about this torsion part? Well, we know that this is, again, the Eisenstein conjecture, that the product of this Fi, which appear here, is just, well, now we take the index of this cohomology class, of the lambda module generated by this cohomology class, inside this inverse limit. You take the limit of this thing, you have this lambda module, and well, I should write, this is a torsion lambda module, so the characteristic ideal of this torsion lambda module, this is again the characteristic ideal, is S. So it's just this guy. No, I mean, you have this X is the Pontryagin dual of the discrete module. So in general, yeah, so in general, this X is going to have torsion. This S is going to be torsion free. That's the, so these are two different, they have the same rank, rank 1, both of them, but this one is, if you take the Pontryagin dual of this guy, of this one, this is the discrete thing. So you are taking a discrete module. Here you are taking the compact one. And these two are related, but actually the relation is that S is the homomorphisms of X to lambda. So it's the dual, the lambda dual of X. That's the relation. So they have the same rank. That's the only thing you know. Okay. And this is the characteristic ideal. So always as before, so you write this as a product of lambda over GI. Now you know there is no torsion because, well, both of them are rank 1. And then this is a torsion lambda module. And you have its characteristic power series, which is the, so then this is just the product of this GI. Okay? So the main conjecture again is proven by the same people as before. And Burungale, Castella, Kim tells you that these two are the same. So in practice, that indefinite setting tells you that the generalized index of the Higner point is essentially it gives you the torsion part of this module. Okay, so this is so far something known, and the question that we want to address is the following. The question is, which is the isoclass, pseudo isoclass of this object. I mean, if you take these two lambda modules, torsion, both of them, they have the same characteristic ideal, but they are not isomorphic. Okay, so the characteristic ideal tells you something, but doesn't tell you the isoclass of the object that you are considering. So the question we have is, okay, we know this conjecture. Sorry, I mean, we know this theorem. I mean the Iwasawa conjecture, this one and that one, and which is the isoclass of this. So this is a question which some people addressed before in the case of elliptic curves, for example. So if you take an elliptic curve over K, so you're not looking at anything about Iwasawa thing, but you take an elliptic curve over K, so there are this famous result of Kolyvagin in which he proves that if this Higner point is non-torsion, then the rank of the elliptic curve over K is 1. This is a famous result of Kolyvagin, but in the work of Kolyvagin, so this Kolyvagin not only proves this fact, but he also uses these Higner points that I'm going to describe a little bit better to identify the isomorphism class of the finite group of the finite Tate-Shafarevich group of the elliptic curve. So he proves that this is finite in this situation in which the Higner point is non-torsion, and he describes the isomorphism class of this finite group. So giving you the elementary divisors essentially. Okay. So we use this. So we try to extend this approach to this general situation in which you have, I mean, this lambda modules instead of some finite group. Okay. So for this, so the goal that we have is to understand the isoclass of a pseudo-isoclass, actually. So the class of pseudo-isomorphism that these modules have of this. Okay, so for this, I will be very sketchy, probably, in this in the description of the technology that we use, because I want to concentrate on the type of result that one can hope to find. But I have to introduce a little bit of technical section, which is called bipartite Euler system. This is after Bertolini and Darmon, which first introduced this thing, and then developed by Howard and many others. Benjamin Howard here. Okay, so we first considered an example, which is the motivating example of this notion of bipartite Euler system, and then I give you the formalism, which is a little bit heavy, or at least at the first time you see it, and then I give you some result on the structure of this object. Okay, so the definition is this. We say that a prime number L is K admissible, where K here is an integer bigger or equal than 1. If this prime is split, is inert in K, this is this, okay, doesn't divide this and the conductor, the prime P that I'm fixing once for all, and the discriminant of K. And the third condition is that P to the K divides this number one of the two numbers, AL plus or minus L plus 1, where here AL, if you write F as the eigenform associated to the elliptic curve by modularity. And then this is a new form. So A1 is 1 of level n. And then AL is the Fourier coefficient. So this is the cardinal, I mean, the product of these two, AL plus L plus 1, AL minus L plus 1 is the cardinality of the number of points of the elliptic curve over quadratic extension of FP, filled with P elements. Okay? Okay, so what we do with this thing, we do Ribet level rising, and we do an example here. So the example that one wants to keep in mind to understand this notion, if you never saw it before, if you saw it before, probably you know very well the story. But so the example I want to discuss is very short, is this one. So you suppose we are in definite case or setting, and then so n minus is the product of an odd number of primes. Okay, and let k be fixed as before, and L, you take a k admissible prime. And just for simplicity, I take k equal to 1 here, but the general thing for higher k is a little bit more complicated, and I don't want to explain too many things. So I just do this case, the one admissible prime. And well, then I want to consider L, lambda, which is my p-adical function that I introduced before. Sorry, not the ideal, the p-adical function. And I want to see this modulo p. Okay, this is now is an element in lambda over p lambda. Okay. And now what I can do with this prime, admissible prime here, is to use Ribet level rising, the rising level. What I can find is a modular form G, or say FL, which is a modular form of level NL, which is new at all primes at the prime L, and such that FL is congruent to F modulo P. Okay. In general, you may not be able to find a modular form. This is a true modular form. So, a modular form with coefficients in C. Okay. Well, algebraic integers, and then you reduce modulo P, and you give a meaning to this congruence. Okay. If you work modulo P to the K with higher K, then you have to be careful because not always you can lift in characteristic 0. So you have to work over Artinian rings, and it's a little bit more complicated. But for K equal to 1, that's the situation. And then I have a Shimura curve, XL. This is a Shimura curve attached to a quaternion algebra B of discriminant n minus L. So notice that n minus is a product of another number of primes. L is prime to n minus. So this is a product of an even number of primes, all in all. And then this is there is the unique indefinite quaternion algebra of that discriminant. And this Shimura curve is just the analog of the usual modular curve. It's just a curve, really. And yeah. So in this curve, we have Wigner points. So notice the following thing here. So we are in the definite situation. So this means that here, the elliptic curve over K has rank 0. This means that, in this case, the rank of EK, so EK is torsion, say. EK is just torsion. So you don't expect to be able to construct interesting point on this curve because they have to be, the Higner point is torsion in this setting, okay? So, and moreover, you can prove, this is Colli-Wagner result, that this is just torsion. At least if you assume, for example, you assume that the L function is non-zero, okay? So I'm not going to talk about, I mean, it might be possible that this L function is non-zero. Sorry, 0, and then we'll have order of vanishing at least 2 by, and even in any case. But let's assume to be in the simplest possible situation, which is the one you expect statistically, which is this situation here. And then we know that this is torsion, and then you don't expect to have points, okay? But to control the Semmer group, you need cohomology classes. And then what you do? You put yourself in a situation in which you have points, so you can construct cohomology classes, which you can use to control the Semmer group, even if they do not arise from any kind of points here or any kind of extension, field extension of K, okay? So that's the strategy. So I'm going to consider this Shimura curve. And now in this Shimura curve, I have Higner points on XL, say Kn, which are defined, I look the cohomology classes of these points. These are in H1, Kn, and you take the Tate module of this Jacobian of XL. So you take the Shimura curve, you take this Jacobian, you have a way to embed the Shimura curve into the Jacobian, and then you take these classes, with these points, you look at the Kummer map of these points, you get classes, and via the congruence, using the congruence, this congruence, you get finally some point, some class in the p-adic Tate module of the elliptic curve over P. So the P torsion. The P torsion of the elliptic curve. Okay? So that's the strategy. So you have a situation in which you don't have points, you put yourself in a situation in which you have points, and then you get cohomology classes. And the crucial thing of these cohomology classes is that they satisfy some reciprocity law of these classes is that, okay, if you take the localization at this prime that you have chosen, L, in Galois cohomology, so you're looking localization here, this goes into Kn, and localized at a prime lambda above L. So this is a local cohomology group, L. And then if you look at this class K, okay, Kn, this is just for simplicity, let me only consider the first class. So I want to consider K1 here, but you have a more general version that I just skip. This is just this element lambda. Okay? You have a more general version in which, of course, you have to mod out this lambda, which is an element of lambda over P lambda. You can project to, I'm sorry, maybe I should write this better, sorry. I'm trying to skip the days, but I need to write something. So I need to define this element K infinity as the inverse limit of all this Kn, which is an element in now H1 K infinity P, the inverse limit with respect to the norm maps, the co-restriction map as before. And then the reciprocity law tells you that if you look the localization at the prime L, you're looking at some cohomology group, and then you have that this localization of this class is just your element lambda. Okay, so that's modulo. Of course, everything is modulo P. Okay, so this is the motivation and the example for constructing a bipartite Euler system. So for this, I'm just try to be quick in defining in this notion because it's a technical notion and I don't want to lose too much time on this. But the idea is the following. So you rise the level in 1 prime. Where is it? You rise the level in 1 prime, and you get some other form, FL. So now you can keep going. So you can lift FL in another prime, L prime, and then you have another form which is congruent to the original one, but now you have 2 primes. And then you can keep going. You can still lift this second form with 2 primes, taking another prime, and then you have a form which is congruent to the original one, depending on 3 primes now. And the parity always change, because these 2 settings are completely different. One is this one, and the other one gives you a Schummer curve. So every time you skip by, you add 1 prime, you change the arithmetic situation you are considering, okay? And you can do this, of course you have to verify that your Ribet theorem can be applied in all situations, but we need, one requires some assumptions on this, which are mild assumptions that are not going to discuss. But if you do this, what you get is a collection of classes indexed by square free product of these admissible primes, which have different meaning, in a sense, for even or odd number of primes dividing them. Okay, so this should motivate the notion that I'm going to introduce, and then 3 minutes, 5 minutes, and then I will discuss a couple of results. So we let, and I mean, I will just, for brevity, I will just discuss one of the 2 cases, probably the indefinite case, the definite case. So let nk be the product of distinct k admissible primes. So you take all of them, and for n in nk, let n be this number of distinct of primes, number of primes dividing n. Okay. So we always assume that 1 is in nk, and we put n of 1 equal to 0. So it's okay. So we consider 2 subsets. If n is odd, so this is we are in the definite setting. Then we put in this case epsilon equal to 1. And we consider the 2 sets, nk epsilon and then nk epsilon plus 1. These are those n such that n is odd. And these are those n such that n is even. Okay? And if you are in the indefinite setting, you do the opposite. This is, I mean, I hope the example I gave you simplifies or makes it easier to understand this notion. But when It's the notion of change of parity that I was talking before. So if ni is even, then we are in the indefinite, yeah, maybe, yeah, maybe I call this indefinite setting. Then in this case, you do the opposite. So you take epsilon equal to 0, and then you have this. These are the n. The n is even. I think that's the opposite, yes. And nk epsilon plus 1 are those is odd. So what you notice is that in these settings, here, 1 belongs to here, the set of even to the nk epsilon plus 1, to the set of even ones, and here 1 belongs to here. So we are really in a different situations. And the bipartite-Euler system is a collection of two classes. So this K is a collection of classes Kn, which belongs to this inverse limit of H1 Km E over P to the K E for n in nk epsilon. And the classes, which are supposed to be in any of these two settings, definite and indefinite, the classes that you get from Shimura curves in the example, okay? When you keep going, rising the level and then you have this lambda, which are the lambda n, lambda over P to the K lambda, for n in this nk epsilon plus 1, which are supposed to be the p-adical functions, modulo P to the K. Okay, so this too has to satisfy some reciprocity law. There are two reciprocity laws. One of them I already mentioned. So if you take n here in nk epsilon plus 1 and you take L which does not divide n, then you have that lambda n is connected to the localization of the classes of the class kappa and L. Okay, as ideas. So these are inequality as ideas in lambda over P to the K lambda. And so this is the first one. And you have a second one, which is one that I didn't mention but also works there, which is the opposite one. So if you take n in nk epsilon and again L which doesn't divide n, then you have that this lambda n L is just the localization at L of kappa n. Okay? So all of this gives you the so-called bipartite-Euler system, and then I will be very brief in saying which is our result. We use, in the similar way of Kolyvagin did for elliptic curves, we use this machinery to control the fitting ideas. So first of all, we define this CAK, these are ideas, so these are the results. So we take this as the ideas generated by lambda n for all n in, again, you fix k is an integer here, and you consider these ideas in lambda over P to the K lambda. And you take the inverse limit of these ideas. Take the Ci as the inverse limit of this Ci. Okay. And this is an ideal of lambda. It's an inverse limit of ideas. Okay, so I will talk only about the results on the definite situation, which is this one, but we have similar results in the indefinite situation. So I have a couple of definitions, easy definitions from commutative algebra, and then I can state the result and then I stop. So the first thing is that if I have two ideals of lambda, we write that they are pseudo-isomorphic somehow if there exists ideas, A and B ideas of lambda, such that of height 2, ideas of lambda of height 2, such that, well, AI is contained in J and Bj is contained in I. Okay, this is the notion of pseudo equality, say, of these ideas up to things of height 2. And also, let me recall what are these fitting ideas. Maybe you already know this, but so you take R is a commutative ring with unit, and M is a finally generated R modulo, and you find you fix a presentation of this form. So you have phi for suitable n and maybe I write h here, n and h. This is a presentation of this module, and you take A, the matrix of phi with respect to chosen basis, and what I'm going to define is independent of this choice. You can take the canonical basis here, and for an even integer, so for a given R integer, we'll define the ER of A. This is the ideal, the R ideal generated by the R times R minors of A. Okay, and then you define okay, if with the obvious constraint that if, so you put ER A equal to 0 if R is bigger than the minimum of this N and maybe H I call it. So yeah, if there is no minor of order R, you put 0. Okay, so then the fitting ideal is fitting ideal of M is given by this I. So the definition is that the fitting ideal I for any integer I, this is of M, this is just En minus I of A for I less or equal than N, and R if I is bigger or equal than is bigger than N. Okay, so the proposition that one can show is that so that pseudo isoclass of a finite generated lambda module is uniquely determined by the pseudo equality class of these fitting ideals for all I. Okay. So the knowledge of this fitting ideal gives you the knowledge of the of the class. So this is more or less known, I think. And then the theorem that I want to conclude is the following. So you remember we used this CI. We defined these elements, these ideas. CI. These are essentially, just state the theorem and then so the theorem that we have is the following. We consider only the definite case. For the indefinite case, okay. Then the fitting ideal of this thing is just ci square if I is even, and this ci minus 1, ci plus 1 if I is odd. Okay, so I don't want to discuss the indefinite case, which is very similar. Just one remark that I'm not going to write much, but even if these CI are only defined in terms of these lambdas, it is the relation of the lambdas with the kappas. So it's really the fact that the bipartite system is made of two distinct sets that make it possible to prove this result. And for this result, we use the strategy of Mesurubin, essentially. So what we do is, first we study the case of Artinian rings of these bipartite systems. Then we look at case of DVRs. And then we look at localizations of lambda at high prime ideals, which are DVR. And then, we put all the information that we have on these specializations at all height 1 prime ideals of lambda to deduce this result. Okay, I think my time is gone. The one other thing, the last one, is that similar results have been obtained in different settings. So in classical Iwasawa theory by Kurihara. The crucial difference is that if you know this kind of results, is that Kurihara in a different setting, not for elliptic curves, requires the representation that he works with that are not self-dual, while here the self-duality of the representations are essential for this interplay between the lambda classes and the kappa classes. So it's okay. Maybe I stop here. Thank you for the attention.
Any questions or comments?
Yeah, exactly. Yeah, exactly. These things, I mean, when you, if I understand correctly your question, when you specialize this thing, these are the elements of lambda. When you specialize this thing at high prime ideals of lambda, for example, and your specialization, you land to some twist of elliptic curve, for example, by some finite order character. What you get is exactly the Euler system that you would define starting from the elliptic curve twisted by the character. I don't know if I. So these are you can recover exactly the structure of the finite Tate Shafarevich group. Yeah. Exactly. Yes. Yeah. Yes. Sorry, maybe I didn't understand the question, but yes. So you can distinguish. Yeah. That's what I was mentioning. Yes. And that's what you use with this strategy of Meso-Rubin that I was telling. So yeah, it's a strategy from Artinian, DVR, and then lambda. So that's the strategy. So for that, you need this to specialize well, to control the specializations.
Any other questions? Comments? If not, let's thank Matteo again.
Thank you.